In Chapter 6, we are going to look at the idea of an isomorphism. And example 1 illustrates what we mean when we want to decide if two groups are isomorphic. So let's look at example 1. And what I'd like you to do is I'd like you to do it on your own and then come back and then we talk about it. So we have two groups here. We have the group G that consists of the numbers 1, 2, 3, 4 under multiplication mod 5. And then we have the group G bar, which is rotations, R0, R90, R180, R270. So the group of 90-degree rotations and its powers. The question is, should we count these two groups as differently or not? And so for that, you want to look at the two Cayley tables over here and see how are these two groups similar, what's different about them, how do they compare? So if you haven't done so already, stop the video, think about it for a minute, and then come back. Well, so here we have G, here we have G bar, and the question is, are they similar? What are the similarities? What are the differences? And some differences, for sure, well, G consists of numbers, so elements are numbers. And for G bar, elements are functions. What else is different? The group action is different. So here, it's for G, we have multiplication mod 5. And for G bar, the group action is function composition. But this is where the differences end. And if you look at them a little bit more closely, both groups have 4 elements. And you can identify elements in G with elements in G bar that really correspond to each other. So for example, if you're looking at 1, the element 1, it really behaves like R0. It's the identity for the group. And then if you're looking at the element 2, it behaves a lot like R90. So for example, 2 times 2 is 4. We get this entry right here. R90 composed with R90 is R180. It behaves very similar to this. Similarly, 4 behaves like R180 and 3 behaves like R270. So we have this natural one-to-one correspondence between elements in one group and the other. So among elements in G and G bar. And the correspondence is 1 behaves like R90, 2 behaves like, 1 behaves like R0, 2 behaves like R90, 3 behaves like R180, and 4 behaves like R270. And the function action, we can even include that. So with that I mean, when we are identifying elements in G with elements in G prime and do the group action in G and then see what does the corresponding group action in G prime look like, they also correspond to each other. So let me see what I mean. So if we have 2 times 3 mod 5, that is 1. And in G bar, the corresponding group action would be R90, because that's what 2 corresponds to, composed with R270. And that is R0. And so we have the correspondence 2 corresponds to R90, 3 corresponds to R270, and the outcome also corresponds to each other. 1 corresponds to R0. So we are kind of keeping the group action with us under this one-to-one correspondence. Or another example, if you take 3 and you compose it with itself, you multiply it by itself, mod 5, you get 4. And the corresponding action in G bar is R270 composed with R270. That is R180. And that is the same thing again. So R180 corresponds to 4. So 3 corresponded to R270, 3 corresponds to R270, and then 4 corresponds to R180. So we have this one-to-one correspondence preserved under the group action. So this correspondence, identifying one element in G with an element in G prime and G bar, that is an example of an isomorphism from a group to another. So the definition says an isomorphism, phi, from a group G to a group G bar is a one-to-one function from G onto G bar that preserves the group operation. So phi of A times B is phi of A times phi of B for all elements A, B, and G. We saw 2 examples of this right up here. And I'm going to write it down in example 2 a little bit more specifically. But if we have this one-to-one and onto function from G to G bar, then we say that those 2 groups are isomorphic. And we use this notation right here, the G with a twiddly equal sign, G bar. So that means is isomorphic too. Those 2 groups are isomorphic. And I think we can just go on to example 2 to finish up this idea of an isomorphism preserving the group operation. So in example 2, let's write down our isomorphism from G to G bar from our earlier example. We can define it one element at a time. So we can say phi of 1 is equal to R0, and phi of 2 is equal to R90, and phi of 3 is equal to R270, and phi of 4 is equal to R180. And it's important to do it in this order, so that the group action is actually preserved. And if we are doing it this way, we see that phi of 2 times 3, let's see what that is. Well, 2 times 3, that's 1 mod 5. So this should be the same as phi of 1. So I'm doing the group operation in G first, and then I'm applying phi to it. And phi of 1, we said, is R0. So this is what's happening when I do the group action in G. Now let's do it the other way around. Let's look at phi of 2 times phi of 3. What is that? Well, phi of 2 is R90, going back to my isomorphism. Phi of 3 was R270. So when I compose those 2 with each other, I get R0. And you see, it didn't matter if I did the group operation in G. So right here, the group operation happened in G. Or if I do the group operation in G bar, the outcome is the same. I get equality of those 2 things. And let's look at one more example. What if we look at phi of 3 times 3? Well, if I do the action in G, I look at 3 times 3 mod 5, that is 4. And phi of 4, according to my isomorphism, it's R180. If I do the group action in G bar, I first look at phi of 3 times phi of 3. That is R270, R270, and well, the composition of R270 with R270, that is R180. And again, we see that those two are equal. And you could convince yourself that this is true for any. So this is true for any A and B in our group G. We get that phi of A times B is phi of A times phi of B.